for the invitation to speak in your seminar. I'm very honored by this invitation. Okay, so the title of my talk is Lattice Gauge Theory, Combinatorics and Surfaces. Okay, and I have to say that I'm not an expert in lattice gauge theory and in physics in general. I just started thinking about this topic because I started talking to my high school classmate who is a physicist specializing in lattice gauge theory, and he does some mathematical physics as well. And so we started talking, and this is how we started working on this problem. So if you ask me very difficult physics questions, I will not be able to answer, but it's a joint work with him. His name is Vladimir Chelnokov, and anyway, if you have questions about physics, I can ask him. I can pass your questions to him or something if you have like really physics questions anyway. Okay, so some disclaimers that unfortunately this talk, it's a kind of new joint work in progress, and it doesn't have a lot of results. It only has kind of questions, observations, and kind of guesses or conjectures, I don't know. So, I mean, I could have given talk about some of my older work, but I decided to give a talk about this new work because I like it more than my old work. So I decided to give it, even though it's very raw and it's not very polished. So it's probably not very appropriate for a job talk, but I just decided to try this talk because I like it more than my old work. Okay, and also I'm afraid that the talk might be shorter than 50 minutes because
Galia, I never heard someone complaining if the talk finished after 49 minutes instead of 50. I did hear people complaining for 51 minutes. So...
Yeah, and yeah, if you're bored, feel free to leave anytime. I will not be offended at all. Okay, okay, so first part of my talk is about the physics problem in lattice gauge theory that my friend Chelnokov is trying to solve, and what is the background and what progress he made on this problem. Okay, so here is this partition function from lattice gauge theory. So my understanding is that, so it's a kind of Gaussian integral. So it has some exponent of some, so you have some unitary matrices. This is U of n lattice gauge theory. Okay, I will not explain what lattice gauge theory is because, I'm not an expert and probably my explanation wouldn't be very good. So I'll just focus on, so I mean, this kind of theories, they have partition function, which is like the most important quantity for this theory. And for this particular U of n gauge theory, it's embodied by such a Gaussian kind of Gaussian integral of the kinds that occur in probability. So, so what are the notations in this integral? So beta is a parameter. Well, it's a kind of constant, but these physicists, they like to take derivatives in this parameter. So it's a kind of parameter. And the product is over. So basically in this lattice gauge theory, to each edge, so there is a lattice, so underlying everything, there is a lattice, which is like a hypercube lattice. But we will mostly think about the two-dimensional case. So it's basically just a kind of square grid in the plane. And to each edge of the lattice, so to each one-dimensional cell, like edge of the graph of this lattice, corresponds a unitary matrix. And so the sum is taken over all two-dimensional faces P of this lattice lambda. So we have this lattice lambda. L denotes the edges of this lattice, the one-dimensional faces, and P denotes the two-dimensional faces. They're also called plaquettes. in this lattice gauge series, the two-dimensional faces. And UP is the product of UL for all L going around the 4 edges of P. So basically, on each edge, you have this unitary matrix, and then you go around the square in the lattice, a square cell in the lattice, it has 4 sides, and you take the kind of directed product of these 4 matrices on each side of this square. And the integration is with respect to the Haar measure on the unitary group. So something like this. And this is the real part of the trace of this. Anyway, so it's some complicated Gaussian integral kind of. So they're in this physics series, they're interested in studying this integral, and well, they're interested in calculating it, but I guess it's not really possible to explicitly calculate it. So they're interested in, well, understanding it as well as they can. And for this purpose, they usually distribute it into a series kind of. So, okay, yes, now I'm supposed to say some words about physics. So I don't really understand physics very well. And but let me just, this is what I understood from what Vova Chelnokov explained me and from reading some papers anyways. So, okay, so again, so like I said already that, so we have this parameter beta, and in principle, we want to consider this integral as a function in beta, and we want to take derivatives in beta, which give phase transitions for this model. And we want to make sure that all the summands in the partition function are non-negative. This is another. So basically, physicists, they try to distribute this in, I guess they Taylor expand it in beta, and then they also do some other expansions, and you get an expansion into a series, and you want all the terms in the series to be non-negative. And there is a more complicated physics problem related to this problem when you add fermions to the theory, and then the partition function becomes a more complicated integral of a similar kind. And anyway, so this is like a more basic problem which can be made more interesting by adding fermions. And
yeah, excuse me, I have a quick question. So what do you mean by wanting to make sure that the summands are non-negative? I mean, what
okay,
are
I didn't write the summands, but there is some way to expand it into a series, and the terms in the series, the coefficients of the terms in the series should be non-negative. It's called sign problem anyway. So I mean,
so this is a conjecture that they are non-negative, or there are parameters that you need to choose to make it so?
I think it's more like a conjecture, yes. But they don't state their conjectures explicitly. So I'm not, I'm sorry. I can ask, well, Vova Chelnokov more precisely, and I can email you the answer later, because what I say probably will not be very trustworthy. Yeah.
Okay.
Thank you. Yeah, maybe if I'll send you an email or something. Anyway, yeah, thanks. And
Okay, thank you.
sorry about this. Yeah. Okay, so then there is this technique called Weingarten integration. So it's for calculating integrals of this type, and well, okay, I probably will not explain it here because it's quite cumbersome expressions, but basically the idea is that you start with this kind of Gaussian integrals, and you will, it was invented by Weingarten in studying some kind of physics, like some quantum field theory or something like this. So they kind of start with this like Gaussian integrals, and then they kind of expand them, they integrate them in some variables and expand them in some series, and they get some complicated combinatorial expressions. Anyway, it's some technique called Weingarten integration in physics, and I will not review it because it would take a long time, and these expressions are very cumbersome. So I didn't find a good way to review it during the talk. So anyway, So yeah, so anyway, so if we apply this technique of Weingarten integration, which is some technique for calculating such integrals and expanding them into a series, then we will get something like this. This is like some horrible formula. But the point is that instead of some expressions with integrals, we get combinatorial expressions with, well, series, but the kind of terms of the series are they're very combinatorial expressions. They're no longer integral signs or anything. It's just a series with very combinatorial terms. So let me review what the terms are. I'm sorry, this is a very, very cumbersome formula, but the point is that there's nothing very complicated in it. So, okay, so the kind of the beginning of the formula is just some, delta, which is just a Kronecker delta with some indices. This is also some coefficient. It's a series in beta. I mean, it involves some Taylor expansion as well. So we had this parameter beta, it's still here, and these things are just some integer parameters, k and k prime. And so the kind of significant part of this expression is the kind of tail, the last part is basically, okay, so there is some Weingarten, something called Weingarten function, which, okay, this technique is called Weingarten integration, and it produces these things called Weingarten functions. So this Weingarten function is something very nice and interesting. It's for a symmetric group, basically. That's where combinatorics enters in, and it enters in the form of symmetric group. So we have this Weingarten function, so n is just the kind of u of n, the n in the u of n gauge theory. So it's the size of the group for the gauge theory. So it's Weingarten n of sigma, so sigma is a permutation. So in this sum, sigma and tau are permutations. And basically where permutations come from is just that when we do these expansions of these integrals into series, we kind of expand these matrices into matrix coefficients and group them together. And these permutations come from these permutations of indices on these matrix coefficients. When we expand these matrices into series and Taylor expands them and regroup everything. So that's where we get permutations, basically. So that's why we have this sigma and tau permutation. So this is sum over some permutations, sigma and tau. And oh yes, and also what are the indices in this horrible formula? So P are these plaquettes, these are the squares of the lattice, L are the edges, the one-dimensional cells of the lattice, and H are vertices of the lattice. Yeah, H are vertices of the lattice. Okay, so vertices of the lattice, edges of the lattice, and squares, plaquettes of the lattice. Okay, so these are the indices, and what are these Weingarten functions? Weingarten functions are, well, so sigma is a permutation, so it's 1 over size sigma factorial squared, sum over all, well, partitions lambda, which partitions the size of sigma of the numerator is the dimension of this irreducible representation of the symmetric group corresponding to labeled by the partition lambda. So you know that, well, representations of the symmetric group are irreducible representations of the symmetric group Sn are labeled by partitions of n. And this thing, and okay, there is some formula, some hook length formula for the dimension of the irreducible representation corresponding to the partition lambda. Okay, and so basically, so this numerator is something nice, and so you take this lambda, which is irreducible representation corresponding to the partition lambda of the number, which is the order, the number of elements permuted by the permutation sigma. So this is dimension of lambda squared in the numerator in the denominator, this is also something very nice. This is, well, Schur functions. Schur functions are characters of irreducible representations of the symmetric group. So, you know, so of course, I mean, you know that, again, what are the, so there are some homogeneous polynomials, right? So of course, like how do, so we have these representations of the symmetric group, which are labeled by partitions, and is there, well, they have characters, and their characters are some homogeneous polynomials in these n variables, and they are precisely, so the characters of the irreducible representations are precisely something called Schur functions. They're very nice, interesting combinatorial polynomials, and here basically we have to take the Schur function for this partition lambda, which labels this irreducible representation corresponding to lambda, and plug in 1, 1, 1, 1, just ones into it. So this kind of thing. And then, and the last part of this expression is the character of lambda at sigma. So by character just mean, well, the character of the reducible representation lambda. Okay. Anyways, this is a very nice combinatorial expression in the symmetric group. It's the Weingarten function, and yeah, okay, and then P, so okay, so this is a Weingarten function, this is what I just said, and the very last part is this P, which is, P is a power sum symmetric function. So again, there are these Schur functions, which are very interesting homogeneous polynomials, but they're very complicated. I mean, they're characters of the symmetric group and of reducible representations of the symmetric group, and they're, well, they're complicated. And the power sum symmetric functions are simple things. They're just sums of powers of each variable, so of the same power to the same power. So there's just power sum symmetric functions. So again, it's some expression for the symmetric group, and they are, so the only complicated thing here is this gamma of h. So gamma of h, unfortunately, is something pretty complicated. So basically the gamma of h, so h is some vertex in the lattice, and it has 4 edges adjacent to it, and these edges are labeled by permutation sigma 1, sigma 2, tau 1, tau 2. Well, anyway, and then L is the left shift, so it's just the cycle which shifts all the variables by some number x. Anyway, so it's some expression of this sort. Anyway, yeah, it will be important later that it's an expression of this sort. Anyway, so this is somehow Weingarten integration produces this kind of formulas for these integrals. But somehow these formulas are not very satisfactory, and the task in this business is to kind of simplify these expressions and kind of try to calculate them more explicitly. So this kind of answer is not satisfactory for these physics purposes because, well, yeah, I guess these expressions in the symmetric group are very complicated, especially with, anyway, so one wants to simplify them. Okay, so now so we have a few ideas how to approach these things, and so unfortunately they're just ideas. We haven't really developed them very far, but anyway, I'll just talk about them. Go ahead and talk about them anyways. So first of all, there is some approach by finite group theory, namely here. So again, unfortunately, I won't be able to write out all the transformations of these integrals because I'm not sure it would be terribly useful anyway. But
sorry, I have another basic question. So what you're looking for is another exact expression, but simpler, or you're looking for an approximation to the?
Well, I'm looking for another, well, I need a series. Yeah, an exact expression in the form of a series, yes. But and they're also interested in asymptotics of these expressions, but as far as I understand. But the first, what we're looking here is just another way to express it as a series with kind of simpler terms in a sense. So something, well, I guess the main thing they want to do is they want to calculate derivatives in beta, and for this, they need some other way to expand it in a series, I guess.
Okay.
Yeah, something like this. Yeah, thank you. Okay, I'm sorry. I'm sorry I am talking about so many formulas. It's unpleasant, but well, I couldn't find a better way to give this talk, so I'm sorry.
Also,
Okay.
I'm familiar with random matrix theory, and there's no way around this kind of formula. Yeah, so that's
okay. Maybe, but we're still trying to simplify this kind of expressions. Yeah. Yeah. I mean, so we're trying to regroup them in different ways and try to find some ways to simplify them. So basically, so here is this kind of try to apply some finite group theory to this kind of things. And sorry. Okay. Sorry. Okay. So, okay, so there is some way to take these horrible expressions of as such as formula 2. So this one that I showed you before. And so regroup these terms so that they reduce to calculate in this kind of expressions in the symmetric group. So in fact, there is some way to reduce them to calculate in some cases to calculate in some kind of expressions of the following form, where you take the following sum in the symmetric group, where you have some fixed permutations. So basically what you do here is like a sum over cosets or something. So there are two cosets indexed by sigma and tau. You take sigma and tau, some fixed permutations, and then you take cosets for these permutations. And you just multiply characters of two corresponding to two irreducible representations, take their values at these cosets, and then you just sum over all the cosets, kind of. I mean, yeah. And this is a very simple kind of expression, but of course, if there was a way to evaluate this expression in general, people would have found it already, probably, because it's a very simple concept from finite group theory. And basically, we found that someone named Reinhard Knorr, who is a German mathematician, he wrote in 2005 a paper where in finite group theory, where they can actually calculate this kind of sums in some cases, namely, but it's not just for the symmetric group, it's for any finite group and its subgroup. And they say that this value of this expression is 0 when two characters have no common reducible constituents when restricted to the subgroup. So in this sum, this is for a group and a subgroup. So you take cosets for things in a subgroup anyway, and you sum, it's the other way around. So you take these cosets in a subgroup and you sum over you take cosets in a group and you sum over the subgroup anyways. So you can do this kind of sum for any group and a subgroup, and well, so Reinhard Knorr knows how to calculate it in case they don't have any common irreducible constituents. So basically we were trying to generalize this to more general sums, and so maybe there is some way to approach it from this point of view. Probably in general, you can't really calculate the sums, but in some cases, his approach can be generalized. Okay, I will not write the precise results, they're pretty messy, but anyway. So something like this. Okay, so this wasn't the main, this is quite a mess, but anyway, there is approach like this. And then there is another approach. This is very interesting, but unfortunately we didn't really complete this approach. So we found an interesting paper. Well, I mean, obviously we knew about this paper, but it's very interesting. This paper has something to do with this, hopefully. So this is the paper of Okounkov and Vershik about the symmetric group. You know, they have this very interesting way to treat representation theory of the symmetric group using, you know, Gelfand-Setlin patterns. And so basically, yeah, like inducing representations, yeah. Anyway, so it's some approach to representation theory of the symmetric group. And we found that it's very interesting that in this paper they have, so this paper has 8 sections, and the kind of the last section is section 8, and it's devoted to Murakami-Nakayama rule, and the main statement used to prove Murakami-Nakayama's rule for the symmetric group is, well, the following statement. It's related to this formula that I showed you. So remember in this horrible integral, okay, sorry, I'm going back to this horrible expression, combinatorial expression for the integral in the beginning obtained by Weingarten integration. So there was this gamma of h, p gamma of h, and gamma of h was this horrible expression, the product of 8 things. So there were some sigmas, some taus, and some L's. So else was the left shift by some amount of units, by some number of units. So there was this interesting left shift. Well, okay, there were a bunch of permutations and a bunch of left shifts. So, so the point was that, well, if you want to simplify this expression, we have to deal with this gamma of h somehow. Okay, which consists of these permutations interspersed with some left shifts by some amount of units. Okay, sorry, I'm going back to this slide. Sorry, I just said these things with words in this slide instead of formulas because I just want to kind of say the general idea of what's going on. So yeah, it didn't come out very good, I'm sorry, but let me just kind of say in words what's going on. So, because, I mean, the exact formula is not, I don't see how the exact formula is so important here. It's just kind of the shape of this formula. So in this Okounkov-Vershik paper about the symmetric group, they have this section 8, which is kind of concrete applications of their theory, namely how to apply it to how to get the statements about symmetric group from their theory. And the main statement in that section, well, they want to prove the Murakami-Nakayama's rule for the symmetric group, but how do they prove it? Well, they prove it with the help of theorem, so-called theorem 8.1 in their paper, which says the following thing, that you want to calculate the character of any irreducible representation of the symmetric group on a shift of the form Lx. So a shift exactly of the form that occurred in this gamma that I showed you in this horrible formula obtained by Weingarten integration. So in fact, so this is kind of the main consequence of this theory in Okounkov-Vershik's paper, how to calculate the character of any reducible representation on this shift of the form Lx. So basically a cycle which shifts everything by x units. Yeah. Okay, so this is how this paper, anyway, that's what it lets you do. And in fact, this is kind of useful for this integral, for this horrible expression that we're trying to calculate, because one has to deal with the character of gamma. So after some manipulations with this formula, with this big horrible formula, one gets character of gamma, in fact. So I'm not going to show what manipulations you do, but somehow you believe me that what comes out is the character of gamma after you do some summations and change the order of summations. Something that comes out is the character of gamma, and well, there are some problems here because, well, so what this Okounkov-Vershik theorem 8.1 gives us is the character of L. So we have to deal with character of gamma, but gamma is the product of several things. Namely, it's a product of 8 things, 4 of which are some permutations and 4 of which are these L's. And L's go like not one by one, but they go one. They're interspersed with the permutations anyway. So yeah, so anyway, so yeah, so the character is not multiplicative for a product of matrices, but one would like to obtain an analog of theorem 8.1 in Okounkov-Vershik for matrix coefficients instead of characters. And so maybe so since one knows that there are orthogonality relations for matrix coefficients, just like there are orthogonality relations for characters of a finite group, this is some standard factor group series. So this is why one can hope to obtain some generalization of this theorem 8.1 and Okounkov-Vershik for maybe not characters, but matrix coefficients. This is probably too much to hope for, but probably maybe some intermediate variant can help us. Okay, so anyway, so we hope that this theory in Okounkov-Vershik will help us with simplifying these integrals, but one needs to generalize their theorem 8.1, and we hope that the same approach as what they use can be used to generalize their theorem, but this is also not done anyway. Okay. And finally, this is a very interesting, this is why I decided to talk about this in your seminar, because I know that Ron Puder works at Tel Aviv University. So because we were reading the papers by Magee and Puder, because they're closely related to these integrals. Well, they treat integrals which are closely related, to which our integrals are closely related. And their papers are very nice because they're geometric, right? So they introduce some geometry into the picture, namely geometry of surfaces. And basically, if we want to relate our problems to these Magee and Puder techniques for dealing with integrals of similar kind. Yeah, so basically Magee and Puder developed some surface techniques for expanding these Gaussian integrals. So they have a series of some very beautiful papers published in like Invenciones and all very, very good, very fancy journals. And anyway, so we just were reading these papers, and we still want to find a precise relation between our problem in physics and these beautiful papers of Magee and Puder, which use surface techniques to calculate similar integrals. Okay. So basically the paper that we were reading is archive 1802-04862. And this is paper number 1 in the series. There is paper number 1 and paper number 2. So this is the first paper in the series. Okay, so they developed some approach to integrals which are close to our integral, which I will write. So in the bottom of this slide, I write their integral. So they also use Weingarten integration initially to distribute this integral into a series, and then they find a way to write down their integral as a series whose terms are indexed by surfaces, basically topological surfaces, like surfaces of genus G, like, and so each term is probably with some, maybe with some maps between the surfaces. So, so the terms are indexed by surfaces, and well, and each term indexed by surface can be calculated in geometric terms as certain L2 Euler characteristics. And well, such Euler characteristics of the kind, like a more foundational Euler characteristics of this type, were studied by Harrer and Zagier earlier in their famous paper. And anyway, so what kind of integrals do Magee and Puder compute? They calculate integrals of the following form. So we have some words, so free words, just some alphabet in R letters, I guess, and some words in this alphabet. So just some free non-commutative words in this R alphabet in R letters. And this basically, the integral is also some kind of integral over the unitary group, some Gaussian integral. Well, no, not Gaussian integral, I'm sorry. It's just some, well, it's also kind of, well, it's an integral over the unitary group over the Haar measure. So also the integration over Haar measure, and basically the integral, so basically you're taking some matrices in the unitary group, and you take these words, you have L words, and you take these words and you plug in these unitary matrices into these words, so you obtain some non-commutative polynomials in these matrices, and you take traces of each of these polynomials in these matrices, and you multiply these traces, and you take the integral with respect to Haar measure, and this is called the trace W1 up to WL of n. Such a very nice integral. And they basically, in these beautiful papers, they find a way to distribute this kind of integral in a series, and this series is not just any series, it's indexed by some topological surfaces, and each coefficient of each of these terms is some L2 Euler characteristic of this surface with some map, like some maybe map, self map of this surface. So it's a very beautiful thing. Okay. And finally, basically, okay, again, I will not show the formulas because they're pretty cumbersome. I have them written down. Vova Chelnokov wrote down some formulas. I have like a document with these formulas. But I mean, there is nothing very complicated involved. So we're going to Taylor expand in beta. We can Taylor expand this initial partition function integral in beta and regroup the terms somehow. So it's just some regrouping of terms. It's nothing very complicated. No big ideas involved anyway. So, and then we can distribute these integrals, this partition function, into these integrals of the Magee-Puder types that I just wrote down for certain words. So, and then the question is, so what are these words? So some Volodya Chelnokov, he computed some examples of these words, and so we're going to compute probably some more examples, but the question is, so he thinks that it would help him with his problem if he understood what exactly surfaces, for instance, enter into this kind of expansions. So basically, he can expand his partition function into a series with terms that are Magee-Puder integrals. And basically, the question is, which Magee-Puder integrals do we get in this expansion? And we do get them for certain words and for certain words, and these words can be calculated, but what surfaces do we get when we further expand them in this Magee-Puder way? This is a kind of interesting question that we're trying to answer, and maybe we would appreciate comments from maybe Daron Puder, or anyway, some people who understand these things. And And the last question, which I think is very interesting, is whether there is some relation between this Okounkov-Vershik approach and this Magee-Puder approach, but this we completely didn't study, and we think it's an interesting question anyway. Okay, so this is it. Thank you.
Thank you very much, Galia.
Thank you.
So are there questions? We have time for questions. I think that Magee is also here. Is it possible? Yeah, so you asked for Doron remarks, but Magee can maybe also provide some insight.
Yeah, I think he's here. Yeah. Perhaps after we can talk later. Not in this forum, I think.
Thank you very much. Yeah, I'm very interested in talking about this with you. Yeah, thank you.
Did you try to calculate the first term or second term? So I mean this, your first question.
Oh, in the first question about finite groups here?
No, about this Magee-Puder integrals which appear in expansions. Yeah, so but there are kind of terms of lower order when maybe it's simpler.
Oh, I can show you an example. One sec. Okay, this example is pretty cumbersome, but since we have time, I guess we finished earlier. I guess I can just show you an example. Okay. I didn't want to show because it's kind of cumbersome, but I can just a moment. Since we're already talking about it, then it's better to see an example because I don't see how I can explain this stuff without an example. Okay. Here. So there is an explicit example here. All right, this is this derivation of this expansion of the integral of our partition function into this series in this Magee-Puder integrals trace W of n.
Yeah, are we supposed to see something?
Oh yeah, I'm sorry. I'm gonna share the screen. I'm sorry. I'm confused. Yeah, I thought I was sharing the screen, but I guess I'm not.
No, you only share the PDF file.
So you should unshare and then share new screen.
I'm sorry, I'm confused. Yeah, okay, just a moment. Sorry about this. Now, is it okay?
Yes.
Oh, okay, sorry. So this is just some PDF. This is just a 3-page PDF document here. So here you have this partition function to begin with. This is the same as my formula 1 in the slides. And here is some derivation of the expansion into this Magee-Puder integrals. Anyway, so it's some regrouping of terms, I guess. I don't think it's terribly enlightening to think how it's done. It's some regrouping, Taylor expanding plus regrouping. And in the end, we get some series in this trace W of n, which are these Magee-Puder traces, Magee-Puder integrals, where the word set is something like this. So you do get some, you do get some matrix coefficients of these unitary matrices and some indices, and you form words out of these matrix coefficients. And these are the words in this Magee-Puder integral. And oh my God, this is, okay, so this is an example here. Now you see it's kind of horrible. That's why I didn't put it in the slides, but now you can see it. So here's an example for d equals to 2, L equals to 2. So it's I guess it's a shift in 2 places, and we have 8 u variables and 8 k variables. So here is this expression, formula 10 is the expression of this partition function in terms of, in this example, this is the expression of this partition function in terms of this beautiful Magee-Puder integrals, but these words that you use for them are, well, kind of, you know, cumbersome things. So there's lots of them and they're quite, well, you see what it is, right? Yeah, so this is the kind of thing you get. So this is an example, you can compute. The question is, what are the surfaces? So we can compute these words, here they are, and we should probably compute the surfaces that enter, but we haven't really done it. And maybe there are smarter ways to compute them. Maybe if I talk to, you know, Magee and Puder or someone who understands these things, maybe there's some smarter ways to do these calculations and to actually maybe, because we hope that if we rewrite this in terms of surfaces, we will get some more enlightening answers, which this thing is kind of, you know, not very enlightening.
Okay, thank you.
Are there any more questions? Okay, so thank you again. Thank you so much. And okay, let me stop that one.